Hello everyone, my name is Zhang from KAIST. Today I'll talk about our work, which is scalable parallel flash firmware for many-core architecture. So firstly, I will use a single slide to summarize this presentation. Nowadays, modern computer systems allocate many resources for the storage access. For example, multiple CPUs can simultaneously send requests to the NVMe driver. The NVMe driver can create up to 64K queues, and each queue can allocate 64K entries to accommodate IO requests. The underlying NVMe SSD also can scale up its NAND flash resources to serve the multiple memory requests, IO requests. However, the SSD controller usually employs a few cores. It exhibits poor performance, which can be performance bottleneck. We can employ more cores in the SSD controller to improve its performance. However, the existing SSD firmware cannot scale well with when we increase the number of SSD controllers cores. So to address these challenges, we propose DRAMless. DRAMless is a scalable parallel flash firmware. It modulates the main functions of SSD firmware into different threads and fully utilizes the multiple flash cores to execute the thread in parallels. Our evaluation results shows like DeepFlash can achieve more than 1 million IOPS in real workloads. I will start the presentation with motivation. We are generating a large amount of data. By the year 2025, the total amount of data will increase to 175 zettabytes. To read the whole data with 1 month, the minimum storage bandwidth should be 1.2 multiplied by 10 to the 10 megabytes per second. If we use the hard disk as a storage medium, it requires more than 4 million servers as storage nodes, and this will generate 4.5 multiplied by 10 to the 10 kilowatt hours per year. Instead, if we can use the SSD rather than the hard disk, we can reduce the number of threads to less than the 1 megabyte per 1 million, and also we can reduce the total amount of energy by 4 times. So to reduce the hardware costs and energy consumptions, there's a high command for the high-performance storage to accelerate the read and the write access. The performance improvement of a storage device is driven by the multiple key technologies. For example, the hard disk has been replaced by the NAND flash. The SATA interface has been replaced by the PCI interface. And the latest trend is we want to adopt the NVMe protocol. It will allocate many resources for parallel access. We expect the performance of NVMe SSD can exceed 1 million IOPS. However, the real performance of the existing NVMe SSD is much far away from our expectations. So next, I will provide a scalable analysis to explain which factors can actually impact the performance of NVMe SSD. Here is a basic computer system which we include in the NVMe SSD. The NVMe SSD is attached to the PCI root complex through the PCI link. The NVMe SSD includes multiple flash arrays which are connected to the flash channels. It also includes a flash controller. The flash controller contains many internal resources such as PCIe module, ECC engine, as well as DRAM buffer. The SSD controller also contains a few cores for the computation. We call this core is flash core. This flash core can be used to execute the flash firmware. Here, I will simply explain what's the main task of the flash firmware. While the NVMe driver creates multiple NVMe submission queue and completion queue in the host, the SSD controller will allocate multiple doorbell registers. When the host submits a command to the NVMe submission queue, the NVMe driver will ring the doorbells in the SSD firmware. Afterwards, the SSD firmware will fetch the commands from the NVMe submission queue. It firstly places the commands into the queues and then pass the commands to find out the address and the data length of the IO request. The SSD firmware also will check if data exists in the DRAM cache. If not available, the SSD firmware will translate the request's logical block address to the physical block address. Afterwards, the SSD firmware will generate a timing diagram based on the request and then leverage the flash physical address to access the underlying NAND flash. Once all the tasks is complete, SSD firmware also needs to compose the completion message and then send the completion message to the NVMe completion queue. It also will inform the NVMe drivers by using the interrupt. Afterwards, the NVMe driver will process the completion message and read the doorbell registers in the NVMe SSD. Each step of the SSD firmware is organized as functions. These functions are called by a single thread through the event-based code. We call this kind of firmware as a layered firmware. To increase the performance of NVMe SSD, we can integrate more number of flash packages so that we can serve the I/O requests in parallel. We examine the performance of flash arrays by varying the number of flash packages. As you can see from the figure, both read and write bandwidth can go beyond 1 million IOPS if we increase the flash packages to more than 256. We also measure the throughput of the whole NVMe SSD device. As you can see from the figure, the overall performance will get saturated around only 180 kilo IOPS. To figure out the root cause of the performance degradations, we analyze the SSD latency breakdown. As you can see from the figure, the flash latency only accounts for 15% of SSD latency when we increase the number of packages to 256. The remaining 85% of SSD latency comes from the SSD firmware. This will include the DMA latency, the address translation latency, the latency of I/O fetching, parsing, and caching. This is because SSD usually employ a few number of cores. It can provide limited computation power to serve the increasing flash packages. So to address these challenges, we can increase the number of cores in the SSD controllers. And also, we can assign each core to execute an instance of the layered firmware. We also measure the performance of SSD controllers by varying the number of flash cores. We expected the performance of SSD controller can be scaled with the number of flash cores. However, the actual performance of SSD controller saturated around only 800 kilo IOPS. This means the existing SSD firmware actually underutilized the multiple flash cores. The root cause of this kind of performance degradation is that many resources in the SSD firmware are shared by all the flash cores. This can include the system memory, flash internal memories, logical block address space, physical block address space, as well as NAND flash access. These resources require lock protections to avoid conflicts from the different flash cores. Although we may have many flash cores, but the access to these resources should be serialized. So this lock became the bottleneck to achieve the scalable performance. To achieve the performance, we propose DeepFlash. It is a scalable parallel flash firmware which are built from the ground. It can achieve the promising storage performance by increasing the thread level concurrency and minimizing the lock impact on the shared resources. Our DeepFlash also is designed to fully utilize the computation of the SSD controller so that we can minimize the number of flash cores. Our DeepFlash modulates the key functions of flash firmwares as hardware threads. For example, the ILOCK threads will be used to control the lock and unlock process. NVMQ threads can interact with the NVMe driver and the pass commands. We use the cache threads to manage the internal DRAM buffer, and we use the trans threads to do the translation of the logical address to the physical address. FCMD threads manage the flash transactions. We also add extra two kind of threads. BGC threads is handle the garbage collection, and the log threads is used for manage the metadata dumping. Our DeepFlash is flexible to scale the number of threads to fit to the flash cores. This is different with the traditional layered flash firmware. We also make the lock-free designs for each thread to enable parallel access. We also make the load balance designs to maximize the flash cores utilization. The I/O request processing can be split into 3 stages. The queue-gather stage includes the NVMQ threads and ILOCK threads. The trans-apply stage includes the cache threads and the trans threads. And the last is the flash scatter stage, including the FCMD threads, BG threads, and the log threads. Compared to the layered firmware, our DeepFlash is flexible to assign different set of threads to process multiple I/O requests in parallels. Next, I will give more details of each thread's design in our DeepFlash. Specifically, I will explain our lock-free designs to how to achieve the high thread level parallelism, and also I will explain our load balance designs to improve the flash cores utilizations. First, I will talk about our NVMQ threads. When the CPU core submits a command to the NVMe submission queue, well, NVMQ will fetch the commands and pass the commands based on the information comes from the commands. It can initialize the DMAs to access the non-continuous memories in the host side. However, when we employ multiple NVMQ threads, the problem is that the NVMQ threads can fetch the same NVMe commands or access the data from the same memory locations. This can generate the conflicts. We design lock-free solutions. This solution is to statically assign NVMe submission queue and completion queue to the different NVMQ threads. However, the different cores may generate different number of IO requests. As a result, it can introduce unbalanced loads in the different NVMQ threads. So, to address the challenges, we propose a load balance-based solutions. The main ideas of our load balance-based main solution is we want to decouple the command fetching and the command passing. We call this solution dynamic IO serialization, DIOS. Specifically, we will allocate the local queue buffers in the storage side, which are identical to the NVMe queue, submission queue, and the completion queue. We also locate two pointer, detail and the deheader, for each queue buffer. The entries between the deheader and detail store the commands which need to be processed. The NVMe we assume the current NVMe S queue and the completion queue is assigned to the NVMe Q0. When the host submits two commands to the NVMe submission queue, NVMe Q0 will fetch the two commands and place them into the queue buffer. This is the same with the previous static assignments. But the difference is in the previous static assignments, we only allow the NVMe Q0 to fetch and pass in all the commands. But in the DIOS, we allow both NVMe Q1 and NVMe Q2 to fetch and pass the commands from the queue buffers. To avoid the conflicts, NVMQ will automatically increase the head values with CPU entries. In this design, similarly, NVMe Q0 and NVMe Q1 both will send the completion message to the NVMQ completion queue, and then only we allow the NVMe Q0 to send the commands directly to the NVMe completion queues. And then finally, the NVMe driver will process the completion messages. In these designs, NVMQ can process. In these designs, NVMQ thread can process our request from any submission queues, so that we can guarantee the load balance in the NVMQ threads. Since the NVMQ threads can access commands from the same NVMe submission queue, it may raise the data consistencies. Here I will give examples. Let's suppose CPU submits request 1 and request 2, and the request 1 and the request 2 both access data a page at address 0x80. Well, we will expect NVMQ0 will process the first request and update the stale data in the NAND flash. Afterwards, NVMQ1 will process the second request and read the data from the NAND flash. However, in reality, NVMQ0 can be stored due to some unknown reasons, and NVMQ1 will access the stale data from the NAND flash. To address these challenges, we introduce ILOCK thread. Let's use the same examples. NVMQ will firstly get the lock from the ILOCK before it can access the underlying NAND flash. And then NVMQ1 wants to process the request too, but it firstly needs to check if the target page has been locked or not. Because the target page has been locked by the NVMQ0, so NVMQ1 has to wait until the ILOCK releases the target page. So in the next step, NVMQ will update the new page and release the page locks, and then NVMQ1 can start to access the new pages from the underlying NAND flash. By doing this way, we can guarantee there is no data consistency issues. SSD usually has billions of pages. Tracking the locks of each flash pages can consume very high cost. So instead, our lock threads organize the lock information in a lock red-black trees. Each node will record the address range which has been locked and which NVMe will own the locks. An NVMe thread can acquire the locks by sending the message to the ILOCK threads. If the ILOCK responds with the failed messages, the NVMQ have to retry and acquire the locks for multiple times. This can consume high overheads. To address these challenges, we propose a lock optimization. Specifically, we propose a forward method. If one NVMQ cannot get the lock, the ILOCK will forward the messages to the lock owner. The lock owner will process the corresponding request on behalf of the NVMQ that do not own the lock. So this design can reduce the communication overheads. NVMQ threads need to communicate with the cache thread to check if data exists in the DRAM buffer. The cache threads usually maintain a direct map table. Each entry will record the logical page number of the stored data and the corresponding location in the DRAM. However, the communication between the NVMQ and the cache can be the overhead because the NVMQ have to inquire for every request. In addition, we cannot allocate many cache threads. In this case, the cache threads can be the centralized lookup overhead. So to address these challenges, we propose to expose a direct map table to the NVMQ so that the NVMQ can check if data exists in the DRAM buffer or not. The cache threads only need to process the cache miss and the cache eviction. Here, I will give examples to show how the cache threads will work. We build a direct map table. Each entry will record the page number of the cached data as well as the data which will be evicted. Let's assume the page 0x00 will be buffered in the DRAM buffer. When the write request 1 comes, NVMQ will check if there's a request miss. And because of this request miss, NVMQ will revise the direct map table by moving the 0x00 information to the evicted LPN. This indicates the page will be evicted. In addition, we also will record 0x03 into the cached LPN. NVMQ will then forward the request to the cache because the cache will do the real evictions. The second request will read the data from the page 0x00. And the NVMQ will look up the direct map table, and it will realize that the page will be evicted. In this case, normal solution will we directly move the read request to the underlying trans threads, but this will cause the data consistency issues. So instead, we will directly send the read request to the cache threads. And the reason we have this one is we want to make sure request 2 will be processed after the cache threads evicted the page at 0x00. The third request will want to write the data at page 0x06. NVMQ will look up the direct map table and find out there is a data miss. Request 3 have to wait for the cache thread to evict page 0x00 and buffer page 0x03. To reduce the waiting times, we will directly bypass the request 3 to the trans threads. And once the cache threads receive the request 1, the cache threads will evict the page 0x00 to the trans threads. The trans threads translate the logical address of our request to the NAND flash physical address. However, the logical address space and the physical address space are shared by the multiple trans cores. So they may need to they may translate the same logical address but to a different physical address. This will cause the conflicts. To address these challenges, we can use the lock-free designs in the trans threads. To enable the parallel processing in the trans threads, we can split the logical address space into chunks, and the pages are spread to the different trans threads by modulating the address with the number of trans threads. Different trans threads also can map their information to the different blocks of the channels through the modulo. However, the problem is if the I/O request is not continuous, it also will generate unbalanced load to the transcodes. To address these challenges, we propose a new design by considering the load balance. We can randomize the pages by using the XOR. By our XOR, the least significant bit and the most significant bit. Next, I will move to the evaluation. Our storage platform uses M5 as a SSD controller. Although it provides 60 cores, but we only use 12 cores as default. And our flash arrays consist of 256 MLC flash packages, which can deliver more than 1 million IOPS. We configure 4 different SSD platforms. 750 SSD and the 4600 SSD are real SSD, comes from the Intel. And we also configure the many layers. Many layers is an SSD platform which creates multiple flash cores, and each flash core can execute one instance of the layered SSD. DeepFlash is our proposed platforms, which including all the lock-free designs and the load balance designs. So firstly, I will show the overall performance. Firstly, real SSD exhibit poor performance when they serve a small IO request. And then when we compare the many layers and the real SSD, it can achieve better performance because we allocate more flash cores into the many layers. And our DeepFlash can optimize the parallel processing in the SSD so it can achieve the best performance. Next, I will compare the SSD control utilization of DeepFlash and the many layers. As you can see from the figures, the many layers has a low core utilization because of the lock issues. But in contrast, our DeepFlash can utilize the most flash cores at the most times, which means we can best utilize the SSD controller. We also evaluate the performance of NVMQ threads by examining the static assignments solutions and our DIOS approaches. As you can see from the figure, the DIOS approach can keep the high performance with various number of submission queues. In addition, with the DIOS, each NVMQ threads can process a similar amount of the loads, which guarantee the load balance. We also set up 4 different ILOCK configurations. Page lock is a method which will lock every page. And ILOCK 1 megabyte will lock every 1 megabyte address range. ILOCK base and ILOCK forward will lock every 256 kilobyte address range. ILOCK forward will enable forward optimization. We firstly evaluate how much ILOCK can impact the parallel execution of the NVMe threads. As you can see from the figure, ILOCK 1 megabyte achieved the worst performance because the locking a large address range can block other threads which access the same address. Page lock actually achieved the best performance. Our ILOCK also can achieve similar performance as the page lock. This is because it does not block the NVMQ. Instead, our ILOCK forward can directly forward the commands to the lock owners. We also evaluate the inquiry latency of ILOCK. Page lock has longest latency as the log arbitrary is large. Our ILOCK forward can maintain a relatively low inquiry latencies. Let me summarize this presentation. There is high demand for the high-performance SSD to accelerate the read and the write access of the large data volumes. The existing layered flash firmware cannot scale its performance with flash cores, which become the performance bottleneck of SSD. We propose DeepFlash. It is a scalable parallel flash firmware for the multi-core SSD controller. It modulates the key functions of a flash firmware into different hardware threads. It fully utilizes the multi-core SSD controller, which can minimize the flash core requirements, and it can parallelize the flash firmware threads across all the cores for the high concurrency. Our evaluation showed that our DeepFlash can serve around 4.5 gigabyte storage bandwidth for the real workloads. Thank you very much.
Okay, questions? There are microphones in the middle here. People have questions?
Hi there. Thanks for the presentation.
By the way, could you give your name and affiliation before you ask?
Jesse Langham. I'm from the Hewlett-Packard Enterprise. I had a question regarding the way you've made parallel thread architectures. Did you also see, with the cores you had in your SSD controller, did you also see some instruction cache benefits in those cores via L1, L2 caches?
Oh, could you explain again?
Sure. Yeah. Well, from what I gathered, your multi-thread operation that is trying to eliminate locking, which is definitely a performance killer. It sounds like you basically had an affinity table that set up the threads to be on specific cores or specific utilizing, not necessarily specific cores, but utilizing very set number of instructions. Did you see, as a result of that, that the instruction cache hit went up in the cores themselves, or were you even looking for that?
Actually, we are evaluate on the real device, so we are difficult to cache what happens in the instruction cache or the data caches. So it might be difficult, but if we can move this to the simulation models, simulators, we may figure out what happened there. So is it answer your questions?
Yeah. Did you have a simulation model that you worked on, or was it basically all just from consumer hardware that you were able to acquire?
Okay.
Good. Xeon 5, then okay. Thank you.
Yeah.
Appreciate it.
Christoph Helvig, Linux NVMe driver co-maintainer. In your architecture, how do you implement the strict arbitration requirements in the NVMe standard that requires strict round robin queue fetches?
Actually, we are adopting the static assignments for the queue to combine the NVMe submission queue, completion queue, and the underlying NVMQs. The reason we want to have that is we want to make it as simple as possible. But we also require to make sure about load balance. So we make another designs to make to fetch the different commands from the different NVMQ threads. So is it answer your question?
No, it doesn't, because when you just have the different queue threads that operate independently, how do you implement the requirement in the NVMe standard that with the default arbitration mechanism, you do a strict round robin through the queues, fetching up to the arbitration burst size from each queue, and then moving on to the next queue instead of allowing unfairness, for example, if one queue gets serviced preferably?
Oh, actually it's not. Because we have different NVMQ threads to access the different NVMe submission queues. So it's not like a round robin to just check one by one.
Yeah, but that sounds like you're not compliant with the standard, but I think I'll leave it at that.
I think we can take that offline. That's a good question. So, all right. I actually do have one question myself. Since it looks like there are no other questions, I will ask one question myself. Looked like from the graph of the number of cores you used relative to performance that DeepFlash was a lot more CPU intensive than what did you call it, many layers? In other words, static partitioning, basically. Does that mean that you have to spend more on CPUs, and wouldn't it be better just to have static partitioning using whatever CPU you have?
Oh, so your question is why the DeepFlash looks more compute intensive compared to the other flash firmware?
Right. Well, more compute intensive per IOP. I mean, obviously, if you get more IOPs, it's going to be more compute intensive. But it looked like it was more CPU usage per I/O than, say, just static partitioning. Oh,
actually, it's not. Because what we want to do, our basic assumption is we will scale up the number of underlying NAND flash resources. So because we have more number of resources, so it requires more computation power to interact with these resources. That's why we create more number of threads in our hardwares. But if we compare to the traditional layered firmware, actually we improve the CPU utilizations. In that case, actually we require less number of cores.
So I have one question. This is Amir Ghulamipur from Western Digital. Did you do any power analysis on how much power your SSD proposal will consume compared to, let's say, Intel SSDs? Oh, yeah. Actually, we consider about power consumption issues, but the current platform we are using, the Xeon 5, actually it's quite unfair to compare Xeon 5 with the actual SSD controllers in the real device, because the actual SSD controller, they use the ARM cores, but we use the more high powers Intel CPU cores. But what we expect is we can make, in future, if we want to make it as a real product, we can put our firmwares into the real ARM cores. In that case, we can achieve also promising power consumptions. Yeah, because one issue there is actually SSDs with that high performance are out there, but they are more like enterprise SSDs, and the power consumption of those is more like 25 to 35 watts. So, yeah. So, power is really a game changer here, the power allocation that we can give to the SSD.
Yeah. From my understanding is as we increase the number of, we want to increase the performance, definitely we need to sacrifice about the power consumptions. But we also have some studies about how we can save the powers as our current works. And we will show up our results in the next submission.
All right, let's thank the speaker again.